Hey everyone, welcome back, and let's write some more Leetcode today. So today let's solve the problem subarrays with k different integers. This is a fun one, and at first it seems pretty simple. We're given an integer array of nums and an integer k. Return the number of good subarrays, and a good subarray in this case is defined as being an array where the number of distinct integers in the array is exactly k. I don't know why they use the word different. Maybe it's to confuse you, but really it means distinct. As you can see from this array, it has three distinct integers, 1, 2, 3. So consider the first example here, and let's say k is equal to 2, just like over here. I won't go through the idea of, there's n squared different subarrays, so at the very least, that's like the brute force solution, because I've kind of said that the last 3 videos. But that line of thinking will actually be useful for this problem, just like the previous ones. Let's think about it for a second. So if this is the first subarray, this is the second subarray. Now we do have 2 distinct integers. Before we did not, now we do. So this counts as a good subarray. We add one more element, we still have 2 distinct subarrays. Now we add another, still 2 distinct subarrays. So far we've counted 3. We add this element here. Now we have 3 distinct elements. So this is not a good subarray. So what do? Well, based on the previous problems, it kind of seems like a sliding window problem, doesn't it? Keep track of 2 pointers, right pointer, left pointer. And at this point, you can imagine we have too many distinct integers. So let's start shrinking our window. Let's shift that left pointer. Pop 1, left pointer is over here. We still have 3 distinct integers. Pop this, left pointer is over here. Still 3 distinct integers. Pop this, left is over here. Now we do not have 3 distinct integers. So this is now another good subarray. With this method, we counted 4 good subarrays. Now we undercounted, we missed some subarrays. So let's go back and replay that portion, figure out what we missed. So in that regard, this is pretty similar to yesterday's problem. Before we replay that portion, I want to quickly mention how are we going to keep track of the distinct integers? How are we going to know that we have exactly k distinct integers, or if we have too many, how are we going to know how far to shift our left pointer? How do I know to stop at this point? The easiest way, the fact that it's distinct integers, probably a hash map or a hash set is going to be useful. The reason I'm using a hash map is because we are going to possibly have multiple copies of a given value. So with a hash map, we can say, okay, 1, we have 2 occurrences of 1. 2, maybe we just have a single occurrence of 2, like at this point. That's why a hash map is going to be useful. And in terms of like shifting our left pointer, when we have this entire window here, we have 2 occurrences of 1. We have 2 occurrences of 2. We have a single occurrence of 3. Now, as I shift the left pointer, I decrease the number of 1s. I decrease the number of 2s. I then decrease the number of 1s again, and now it's 0. And once it reaches 0, that's when we pop this. And now we've gotten to the point where we only have 2 elements inserted into the hash map. That's how we know this is exactly equal to k, and that's how we know when we can stop. So that portion is not super complicated. That's the easy part. But I want to quickly go back and replay that portion and try to figure out how did we undercount the solution? What can we do to correct that? So this is the first valid subarray that we have. So we count 1. We increase it to this point, we count 2. We increase it to this point, we count 3. As we're doing this, we're only counting the subarrays that start at this element. And so far we've counted 3 of them. Once we reach the 3 over here, we realize there's no more subarrays starting at this element. There just cannot be, right? It's impossible at this point. As we add more elements, there's only going to be more elements introduced into the hash map. So we have to stop. We have to then shift our left pointer. We shift it, let's say, over here. Now, this is still not valid. But if you think about it, that doesn't necessarily mean there aren't any good subarrays starting at this element. So that's what we're missing. We missed this subarray and this subarray as well. Not only that, we missed this subarray as well. So I just pointed out 3 subarrays that we missed. Our original count was 4. If we also counted these 3 subarrays that we just missed, then our total would have been 7, and that's what the result was. So how can we devise a solution that will actually get us there? Well, it's going to be kind of hard considering it from the perspective of counting subarrays starting from each element, because by the time, like we start here, left pointer is here, that's great. Right pointer got here, 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 and then finally here. So we counted those 3 subarrays, that's great. As I shift the left pointer here now, it's gonna be kind of hard to know how many good subarrays are starting from this left pointer. Even if we ignore the 3 for a second, we don't necessarily know how many good subarrays are gonna be starting at this pointer, because even though in this example, it's pretty simple, it's 1, 2, that's not always going to be the case. Consider a slightly different example. Consider if I change this to a 2, 1. Now, in this case, how many subarrays are starting from this element? Well, this is not a good subarray. So actually, we only have 1 good subarray. By swapping the order of these 2 elements, instead of having 2 good subarrays starting from here, which would be these 2, we only had 1. So the order of those elements matters. It's getting kind of complicated now. So let's think about it from the other perspective now. Instead of thinking about it starting from each element, let's consider the opposite. Let's consider counting subarrays ending at each element. Let's just see if maybe that makes it a bit more simple for us. I want to know how many good subarrays ending at this element. Well, so far we just have 1 distinct integer, 1 maps to 1, so it's not a good subarray yet. Next pointer, our right pointer is going to be over here, our left pointer stays here, our right pointer is here. Now we have 2 distinct integers. How many good subarrays are ending at this element? Well, just a single one. It's pretty simple. By the way, not going to update the hash map just to keep things simple for us. This is a hard problem, so I assume you know how to keep track of like occurrences of each element. So I will be ignoring this part for now. I'm going to take the right pointer from here, shift it over here. How many good subarrays are ending at this element? Well, I count 1, but I also count this one as well. How do we know that? How do we know that this is also a good subarray? Because like I said, if I swap this, I make it a 2, then there's only 1 good subarray ending at this element. What's the difference? What's the difference between this example and this example? Well, when you look at it closely, it's kind of obvious. We can shift our left pointer here and the window is still valid in this case, right? Now, if I shift the left pointer here, well, this was valid and this is also valid. That would not have been the case if this was a 2. How do we know that we can shift the pointer? Because the count of this element is not equal to 1, it's greater than 1. That means we can afford to lose this and our window is still valid because we have 2 occurrences of 1 right now. Pop it, it's okay, we still are good. Okay, cool. So continuing with this idea, so far, at this point, I'm gonna shift this pointer here now. We counted 3 subarrays. This one, and then after shifting the left pointer here, we also count this one. Now let's continue with this idea. We're getting close, but I'll tell you, we're still not quite there yet. There still is an issue, and let me show you what that is. So now from here, shift the right pointer here now. This, once again, is a valid window. So far, we counted 4 valid windows. And again, we can afford to lose this too. I'm gonna shift the left pointer over here now. This window is still valid. So far, we counted 5 valid windows. Unfortunately, even with this approach, we missed one. We missed counting a subarray. We're trying to count all the good subarrays ending at this element. Remember, that's what we're trying to do. For every element, count the number of good elements ending at that subarray. We counted this one successfully. We counted this one successfully. But the fact that we shifted our left pointer made us miss this one. So what can we do? Well, this is something you probably wouldn't be able to figure out unless you had seen this pattern before. This is called the sliding window with 3 pointers. If you're new to this, just kind of watch me go through it. Just absorb what I'm about to show you and then try to go back and understand it and implement it yourself. I'm going to keep track of 3 pointers: the right pointer, the left far pointer, and the left near pointer. So initially, the left far and left near are both going to be set here. And same thing with the right pointer is also going to be set here. Now the right pointer is going to be over here. This window is valid, so of course we increment our result, but we do not exceed k, therefore we don't shift either of these pointers, and we also don't have like an extra element, so we don't shift either of these pointers again. So these will both stay here for now. Now, once again, right pointer is going to be here. Now, this is a valid window. This is where things get interesting, by the way. Now, we have an abundance of ones. We have an extra one. So what do? We leave the left far pointer over here, and we take the near left pointer and then shift it to the right. Now you can see why I'm calling it the far and the near pointer. This is important because we're trying to count the number of good subarrays ending at this element. That's what it's all about. And these two pointers are going to tell us how many subarrays there are, because the whole purpose of the near pointer is going to be find the minimum window with at least k distinct elements. So if we have an extra element over here, well, we're trying to shrink the window. So move the near pointer up until this point. Now the far pointer will tell us the max window where we have exactly k distinct elements. Both of these pointers will give us a window where we have exactly k distinct elements, but this one will give us the smallest window, this one will give us the largest window. Now with these two pointers, every time we update our result, we're going to add to the result the difference between these. So add to it a near minus far plus 1. The plus 1 comes from the fact that, like, suppose in this original case where both of these pointers were at this element, of course the difference between them is 0, but we still want to add a subarray, so we add the plus 1. Now in this case, the difference between them is 1, and that would mean we have a subarray here and a subarray here. So far, our result is 3 now. Now, once again, I'm going to take the right pointer, shift it over here. Does it look like we exceeded the number of distinct elements? No, so we leave our far pointer over here. Does it look like we have an extra occurrence of this element? Yep, we have 2 of them. So we take the near pointer, shift it over here. We are trying to minimize that window. And now, what do we add to the result? The difference between near minus far plus 1, so we add 3 to the result. Now our result so far is equal to 6. Once again, we take our right pointer, shift it over here, and this is where things get a little bit interesting, because now we've gotten to the point where we have too many distinct elements. We have 3 distinct elements. We are forced now to shrink the window. And by shrink the window, I mean shrink both of the windows. And so instead of us, we kind of have a choice. We could shift the far pointer if we really wanted to, but that would be a much more complicated solution. I won't get into it. We can be smart and shift the near pointer. And watch what I do. I say, okay, let's pop this element. Let's shift the near pointer over here now. And now this window is valid. Also, what we're going to do is just take the far pointer and move it all the way over here to match where the near pointer is, because this is not only the smallest window ending at this element, the smallest valid window, it's also the largest valid window ending at this element. So now these are equal. This is a valid subarray, so once again, we add 1 to the result. Result is now equal to 7, and that's, of course, the result that we're looking for. This is, again, a difficult algorithm. I wouldn't expect you to be able to come up with it by yourself, and you might have to replay portions of this video, but that's okay. Just kind of let the ideas here sink in, try to apply them, try to run it on a few examples of your own, maybe on pen and paper, or maybe if this makes sense to you, try to code it up yourself. This is a sliding window with 3 pointers. The time complexity is big O of n. We do have a hash map though, so let's not forget to consider that a space complexity as well. Let's code this up. By the way, you can see my notes here. You can pause the video if you were curious how I was able to come up with the solution. But I will say that part of the reason I was able to come up with it on my own is, you can see here, I solved it about 5 years ago myself. So that definitely helped, I think. Let's start with the easy stuff, just kind of the initialization. So we know we're going to have a hash map. I'm going to call it count. I'm going to initialize it to a default dict in Python. That just kind of makes it a little bit easier for us to code up. I'm going to have the result, which of course is going to count the subarrays. That's what we're going to return as well. And we're going to have 3 pointers. Left far, which is going to be set to 0 initially. Left near, which is going to be set to 0. And we're going to have the right pointer, but I'm going to use that within the for loop. like this, because every time we see an element, we of course want to increment the count of that element. So the number at the right pointer is going to increase the count by 1. And of course, if the number of distinct elements, therefore the length of the count, is exactly equal to k, we did determine we can increment the result by taking the left near pointer, subtracting the left far pointer, and adding 1. This much we do know for sure. Now, the other thing is, how do we know when to shift the pointers? Well, there's 2 cases where we would shift our pointers, right? While the number of distinct elements exceeds k. That's one case where we're going to have to do some shifting. There's another case, though, where we can try to minimize the window. And the only case we can do that is if the count of the element at the left near pointer is greater than 1. We have extra copies of that element, therefore we can shrink the window. We can shrink the left near pointer. Let's start with this one. I think it's kind of easier. This would be pretty straightforward. We would of course increment the left near pointer, but not before we update the count of the element at that pointer. So just like this, decrement the count by 1. Since we're only going to decrement the count if we have an extra occurrence of that element, we don't have to worry about popping it from our hash map. So that's why I said this is the easy part. I started with it. Now this is the more confusing part, but we know we chose to shift the near pointer. So that's what we're going to do. We're going to decrement the count of that element. So the number at the left near pointer, decrement the count. And if it reaches 0, if the count of that element reaches 0, let's pop that element. In Python, it's pretty easy. Count.pop of this element at that left near pointer. And of course, we're going to take that left near pointer and increment it by 1. When this loop is done executing, we want to update our left far pointer. But if we do it out here, if we take the left far pointer and set it to left near out here, well, that's a problem because we only want to do this update if this loop executed. So the easiest thing to do is just move this line within the loop. Whoops, just tab it into the loop. It might execute more times than we need it to, but this is just the easier way to code it up in my opinion. So this is the entire code, but don't let it fool you. It's definitely not easy to come up with. I'm going to run it to make sure that it works. As you can see on the left, yes, it does. It's efficient. If you're preparing for coding interviews, check out Leetcode.io. Thanks for watching, and I'll see you soon.